Yeah, let's erase all this stuff. This is not. Okay, I don't even know what I'm connected to. If I'm connected to the screen, or if I'm connected to, what I'm connected to. So there's one section left. Okay, let me see if I can get the. Okay, wait. Oops. There it is. And the next question is, what am I connected to? Okay, hang on. Apparently I'm connected to the board. Probably should have just brought my laptop or something. Do I?
Sometimes that's easier than having to.
Yeah. Because I had, then not only that, I could just, I don't know. Okay. Okay. And get rid of that. Get rid of that. And then all these lights are on. That may make it worse. We already get outside lights. What does that do? That doesn't do anything. What about this? What's that? Why do none of these work? Well, I guess that's about the best we can do for the moment. Okay, current courses. Wait a minute. Okay, spring. Source destination is complete. Huh? Oh no, don't tell me the Blackboard's goofed up. Why is it saying that? I don't know what that means. Okay, let's go to the textbook. I hope it's not messed up. Okay. It says chapter 12. Oh, so the last time we looked at this, it was there. So let's go down past. There's curvilinear, motion projectile, normal and tangent, curvilinear. Okay, here we go. So he's got this weird section. I guess that's viewable. Maybe I can make this go down. Is this one? No, wait. This is this one. I'll make that go down a touch. So it's a little bit. Oh, okay. That's a good idea. Yeah. So get a little bit better view in here, but I still want some light from outside. I'd like to know where I would like to be versus where I'm at. So.
Oh, could we actually finish that one question that we started on?
Which question? Which one was that?
It was homework 2, the last question.
Homework 2, the last question. Gosh, I don't even remember.
Homework 2, question number 6.
Question number 6? Wait, okay.
Yeah.
Was there? Wait. So it was that one.
Yeah.
But did I finish it?
We got pretty close to finishing it.
Okay. I thought I finished that.
How we were supposed to get theta dot and r dot, and then how we use that one equation and plug everything in.
Oh, okay.
So we got pretty far.
Okay. So you got r being 0.2. Let me get that dot off the top of it. 0.2, 1 plus cosine of theta. And then, so maybe right up here, if you look back in the book, you'll see the vector itself, the velocity vector, is this. And And so if you look at it, all you really need is that. Well, in order, generally it's best to list them this way. R, a theta dot, R, and R dot. If you had all those, and mine is at 29 degrees, so my theta is at 29 degrees. So this one, he told you outright, at all times it's 3.2. This one, if you want to put it in as a function of theta, you would have 0.2, 1 plus the cosine of theta. This one, you don't know yet, so what you have to do is you do it in the generic sense. You take the derivative. If you want to, you can list this as 0.2 plus 0.2 cosine theta.
We end up getting 0.2 sine theta dot.
Yeah, so this doesn't have a derivative, but this one does. So if you do it in a generic sense, you got that. Then you realize you need to convert. You need to convert that thing. It says I have a great start on exercising. You convert that by doing this, and so that's a theta dot times 0.2 times the derivative of cosine theta with respect to theta, which will give you a minus sign. Now, what you do is you insert 29 degrees here, and you insert 3.2 there, or whatever your numbers are. And then that will be what ends up right here. So what you'll want to do here is 0.2, 1 plus cosine of 29 degrees. You calculate that out and get a number right here, for mine at least, to do 3.2, 0.2, and then minus sine of 29 degrees. And that'll give you a number. And so then if you just look at those three numbers in this, what you'll have is just this, R dot, which will be, I'll say this is number 2 and this is the number 1. You'll have the number 2 times UR plus the number 1 times 3.2 U theta, and that's pretty much it. So this number is whatever that turned out to be. So this number, whatever that turned out to be, the 3.2 goes there. So then he wants to know the magnitude. So the magnitude is, since these are still, no matter where they are, here's your UR, and say here's your U theta, and they're always 90 degrees apart. And since they're 90 degrees apart, if they were not 90 degrees apart, and there are coordinate systems that are not, but since they are, then the magnitude of V is just going to be the square root of the number 2 squared plus all this, because that's this one, the number 1 times 3.2, and square that. And that's what will go in here in the units. Because asking for velocity, it's got to be meters per second. And that's pretty much it. So there's nothing more to it than that. If, for example, you wanted the complete problem, you would have the acceleration on here as well. And I should have given one with that, but I didn't. So, and in the acceleration, you've got, let's see, what do you have? You have R double dot minus theta dot, okay, R dot, that's a double dot. R, well, wait a minute, then you'll have another one of those terms. anyway, you'll have to take there's an equation in there. I mean, if you wanted me to, I can go through how you get all that, but there's a UR that comes out of the derivative of the U theta, which is R theta dot squared times UR, and then there's a U theta that comes out of the derivative of that term, which ends up over in here. But, and it's the same thing, except when you're doing acceleration, you know, you have to know theta dot. That time you need to know theta double dot, you need to know R dot, and R double dot. So when you're finding acceleration, you need to know all 5 of these. When you're finding velocity, you just need to know these 3. And the reason being is because those are all that's listed in there. So,
Dr. Bailey, what do the dots represent?
the dots are just, you know, so R dot is nothing more than dr dt. That's all that is. It's just, it's kind of like y prime is equal to dy dx. It's just when there's a time down there, they put a dot on the top. And that's pretty much it.
And why was it again that we can just do the square root squared?
Well, because what happens, I mean, I don't know the numbers, but let's just make them up. And then I'll show you an exception to that rule. Okay, so here's your UR, or so let's make UR like this. And let's say the velocity ended up being 3 UR plus 4 U theta. Let's just say that we calculated and that's the numbers we got. And so here's your UR, and 90 degrees of that is your U theta. And so if you look at it, 3, you go 1, 2, 3, the vector is about to here, so that's this length, and that's 4. So if I take that and go 1, that's 2, 3, 4, about to right here, this is, you know, length of 4, and that's length of 3. The fact that these two are orthogonal, meaning 90 degrees, means that the vector here happens to be 5, which is 3 squared plus 4 squared, and the square root of it. So I just made it 3, 4, 5 easy for myself.
So it's just because they're orthogonal?
Yeah, just because that and that are 90 degrees to each other and always are 90 degrees. There are, I mean, and give me a second, let's see if I can find how to get there. I know Wikipedia, and I can't even spell it, but I know Wikipedia has. So there's, you know, here's a polar, those are all, let's see if I can find like a prolate spheroidal or something like that. So there's all these weird, okay, let me see if I can find, here. I don't know if I can, P-H-E-R-R-I-D-S. I know I'm misspelling it. So here, if you look at something like that, it's a mathematical thing. And you look at it, and you're like, oh my God, what am I looking at? And if you look at it real close, he's got what looks to me like a little X, and what looks to me to be like a Y. I'm sorry, a Z. But if you look at it, each place like this, if you look at the tangents,
It kind of looks like a level map.
yeah, and so it turns out that I think this one is orthogonal as well. But you can easily find a non-orthogonal system. And so a physicist or a math person who's trying to solve a problem, now this is a good problem, this is a good coordinate system. If you had two, electrons, and one was sitting up here, Or magnets, same thing. One was sitting here and one was sitting here, and these would be the field equations. If you had a magnet, you would see the magnetic field kind of doing kind of like that. And actually, you can throw iron particles on a piece of paper, put the magnets under it, and you can start seeing the things show up. But there's other coordinate systems, and in generic scenes, if you get really heavy into the math, there's an easy way to generate all sorts of field equations. And like, let's say you had a field equation like this. And at this point, it's pretty obvious that if you did a tangent to here and a tangent to here, that's not 90 degrees. And so when you get into those coordinate systems, then you're like, uh-oh, how do you do that? How do you find the magnitude of that? And that's where you go to law of cosines. Because you got two vectors, so all you're doing is to find the magnitude of two vectors, and it's no longer 90. So, but you know that you can find the angle there, and then you can go about and find that. You can find the angle pretty easily. So, but luckily, all we're dealing with is coordinate systems. I mean, polar coordinate system is really nice because it is nice and orthogonal. And so that's kind of what you're looking for. I wonder if I could find, I'm misspelling that. God, I misspelled that bad. Non-orthogonal. Skewed coordinates. So see if that's great. Okay, so then you're gonna look in, and well, that's a generic thing. I wanted to find, you know what, I probably should have, but I did. Non-orthogonal coordinate systems. Non-orthogonal for dummies. That's kind of cool, but does he give me an example of one? A coordinate system. Those are just the equations that you deal with. That's not the system. Well, look, there's some lecture. I could just, hey, statics. Finding vector components of, oh, that's the Jeff Hansen.
Okay,
oh,
guys,
and he's
the
getting
big game
advertisement
needs
money.
big commercial.
So, Jake, you flying on a hang glider with smoke emitting from your chute.
Is he? How do you know he's getting Pearson
out with a
money?
helicopter wearing jetpacks.
And that's
Oh, is
the
he?
only way to show up big for the big game.
30-pound force is like the resultant, okay? And
Oh, really?
means
Yeah, like
it's a
every-
part of.
the beginning of every
So if
episode.
I add U
Beginning
plus
of
V together, then I get
Oh.
30, okay? This.
So he's going through it right there.
Oh, look.
So he's got to go down there and use law of cosine somewhere.
Oh, angle 45. Divided by.
Well, he's using law of sines right there.
Well, that's all of that.
Oh, he's in ancient days. Look, he's using a calculator. He's not using photomath or something. Yeah, that's okay.
He also really likes doing matrices.
Oh, does he? Well, that's good. That's an important thing.
Yeah, anytime I got like confused on anything, I would go to him.
He had a thing, I don't know, where's he from? He's not
Texas
from,
Tech.
huh?
Texas Tech.
Oh, I thought he was from Pennsylvania or somewhere. Anyway, maybe he was at one time.
He
I don't
has
know.
the Texas Tech like a faculty shirt on some of the episodes.
Oh, really?
Yeah.
Oh, okay. So, I mean, that's the thing. I mean, if you wanted to do this the right way, you would just make a set of 10-minute videos on each thing, and then what you do is the minute you finish that, you'd have to go do an assignment on it. And if you did it that way, that's how you do this stuff right. I'm not doing it right, but I know I'm constantly adapting to a system, so. Okay, so relative motion or dependent motion of two particles, the two particles are two blocks, and they almost always are going to be hanging over a pulley. So first thing he does, you'll notice, is he picks a datum here. So what did you notice? He picks a point that doesn't move to measure from, to measure your block A. He picks another one. It just so happens it's the same point, but it does not have to be the same point, as long as the point doesn't move. Then he draws an arrow to the location of B. The reason CD is colored red is because the next thing he does is he says, I'm going to find the length of the rope. And so, you can call this delta CD, so that's the part of the rope that's red and remains the same length at all times, plus SA plus SB. Now, that's great, but the key is taking the time derivative of that. Does the length of the rope change with respect to time? And I'm doing the dots again. Does this change with respect to time? And does this change with respect to time? And does that change with respect to time?
Is that deformation?
That's actually time rate of change. So in other words, there isn't going to be a deflection of the spring. Of the rope. So it's not going to change its length. Okay, you know it will, but we're in this course, and if you wanted to include that, there are ways to include that. Okay. But,
I just didn't know if that was the same symbol that we were using.
Oh, okay. Yeah, this is a different symbol. So this is just one I made up because you got to have that little red part. And it turns out the red part, the length on the red part always remains fixed. So if this block moves around, all this thing does is turn. It doesn't change the distance of that red. And the length of the rope doesn't change. So what you end up with is this. Okay, that. Or you end up with SB equals to minus, or I'll have to do it that way now. So if SA were positive, meaning that this thing is moving like that, and say it's moving at 1 foot per second, then this has to move negative. So if that's 1 foot per second that way, this is 1 foot per second, but it's going this way. And this is sort of mundane and almost like a stupid example because you kind of look at it and you can kind of tell that's what was going to happen. But if you formalize it by always writing your length of ropes and going through them, you'll find that this pattern will save you many times. And let me give you an example. He has examples there, but we'll just go down to his somewhere. So he calls his, I called it delta, he calls it LCD. So I should have done, and here's his time rate of change. And he's saying the velocity of B is the minus velocity A. Okay, I should have stopped and taken another derivative and shown that the acceleration of B is the minus acceleration A. So here's a standard rope that he's got, and you notice he has the reds. The reds are done. So you could just say, and I'm just going to keep calling them. I'll say the symbols like that for all the reds. So all the red sections. But they're not, if this block moves, those red sections don't change. And that's the reason they're listed that way. So then if you look at it, I got 1, 2 of these. And I got 1 of this. And then I got this. Now, in this you should have recognized that this whole thing should have been painted red as well. Now, there is a chance that, I don't know what he's implying here, whether this rotates, but I think the way he's approaching this doesn't rotate. And so if that's the case, the time derivative of this, and this are all 0. And so what you get is 0 is equal to SB dot plus SA dot. So that means if this is moving to the right at 1 foot per second, then moving to the right means it's going in that direction, and that means SA dot is equal to 1 foot per second. You stick that in there, and then you'll get SB is equal to, move that over, it becomes minus, it becomes SB dot becomes feet per second. So if this moves a foot over, this move a foot per second over, this moves a little slower, actually. A ratio of 2 to 1 slower. So it's a half a foot per second. And that's all these things are.
In what direction?
The fact that it's minus, and that's an important question, the fact that it's minus, your datum, your measurement from the datum is down, is positive because of this. So that means it's minus. So if it's minus, it's moving up. So if this is moving to the right, then that's moving up.
And it's moving to the left, it's moving down.
Yeah,
It's positive.
that's right. And so that's all these things are. You just keep up, you have to keep the datum direction is very important.
So
That dictates your plus and minus movement.
what kind of is a datum?
What
What is a datum?
a datum is a location that you measure from in which the datum doesn't change.
So datum's like a fixed point?
Yeah, it's a fixed point. And so you did that so you basically, remember in physics you had mgh is the energy and you had 1/2 mv squared. And and we're going to get to that later, but you dropped the thing and it increased the energy. And so what you said is well, the mgh here, I'm sorry, the 1/2 mv squared here was the mgh here. So the question was, the h had to have a datum. And so what you do is you just say, well, there's my datum right there. And then I measure up here, and that's h. So if I drop it from 5 or 10 foot, I have to make sure I put in 10 foot here. So there's a datum associated with that. And we'll get to that. That's all. That's the section here called energy. Just 12, 13. I don't know. I think it might be chapter 14, but I can't remember. So he's got another picture of the same thing. Now watch what he's doing here. Okay, let's see if I can scroll down. Okay. Oops, is it going to fit? Okay. Wait a minute. It's the same picture. He should. Where's the... Okay. Here's the other one. He decides that he wants his datum. It doesn't have to... Okay, the other one you notice, it didn't have to match. But this time, let me shrink the screen down a little bit. This time, he has a similar... The same exact picture, but now he's done his datum from here for this block. Again, you just have length plus, okay, I used the delta the last time, plus, okay, what do you see here? Okay, this length is now h minus SB. So if I go up this distance, subtract this, and then I have 2 of those, and then I have plus a h, and then plus SA. So then you take a derivative here of everything. Hang on. Okay, a couple things. L dot equal to the delta dot is equal to H dot equals 0. So if that's the case, what you end up with out of this, you have to stare at it for a minute. 0 is equal to minus 2 SB dot plus SA dot. Now if you move this over, you'll get now 2SB dot equal to SA dot. Now let's say this is moving to the right at 1 foot per second. That means this one over here is moving. Okay, so that means SB dot is equal to, put in 1 here, and you get 1/2 foot per second. Before it was minus 1/2. This time it's positive. So, but the direction that is positive is this for B. The direction that's positive over at A is that, because these match those directions. So I've got 1 going to the right and 1/2 going up. And before it was 1/2 minus, but that's because my datum pointed down. And that's pretty much it. Oh, shoot, I didn't get very far today. We'll start again next time. Well, I had trouble starting the machine. I had, I don't know.